Said we were talking about the four forces. We're having some issues here. Let's see if I can get this pulled up here. So it'll be just a moment. Okay, I finally got that figured out. Okay, so thanks to our pals at Public Broadcasting, we have the opportunity to watch this. Okay, and this talks about the four forces. So we want to use this educational opportunity because it's something that we cannot show you. It's not that we don't, not that we can't, but we just don't have the technology. So this is what we're talking about in what we call the elegant universe. Okay, so here we'll go ahead and get started.
50 years ago, this house was the scene of one of the greatest mysteries of modern science. A mystery so profound that today, thousands of scientists on the cutting edge of physics are still trying to solve it. Albert Einstein spent his last 2 decades in this modest home in Princeton, New Jersey. And in the second floor study, Einstein relentlessly sought a single theory so powerful it would describe all the workings of the universe. Even as he neared the end of his life, Einstein kept a notepad close at hand, furiously trying to come up with the equations for what would come to be known as the theory of everything. Convinced he was on the verge of the most important discovery in the history of science, Einstein ran out of time, his dream unfulfilled. Now, almost a half-century later, Einstein's goal of unification, combining all the laws of the universe in one all-encompassing theory, has become the holy grail of modern physics. And we think we may at last achieve Einstein's dream with a new and radical set of ideas called string theory. But if this revolutionary theory is right, we are in for quite a shock. String theory says we may be living in a universe where reality meets science fiction. A universe of 11 dimensions, with parallel universes right next door. An elegant universe composed entirely of the music of strings. But for all its ambition, the basic idea of string theory is surprisingly simple. It says that everything in the universe, from the tiniest particle to the most distant star, is made from one kind of ingredient. Unimaginably small, vibrating strands of energy called strings. Just as the strings of a cello can give rise to a rich variety of musical notes, the tiny strings in string theory vibrate in a multitude of different ways, making up all the constituents of nature. In other words, the universe is like a grand cosmic symphony, resonating with all the various notes these tiny, vibrating strands of energy can play. String theory is still in its infancy, but it's already revealing a radically new picture of the universe. One that is both strange and beautiful. But what makes us think we can understand all the complexity of the universe, let alone reduce it to a single theory of everything? We have R mu nu minus a half, G mu nu R, remember how this goes, equals 8 pi G T mu nu. It comes from varying the Einstein-Hilbert action, and we get the field equations, and this term, remember what this is called. No, that's the scalar curvature. This is the Ricci tensor. Have you been studying this at all?
No matter how hard you try, you can't teach physics to a dog. Their brains just aren't wired to grasp it. But what about us? How do you know that we're wired to comprehend the deepest laws of the universe? Well, physicists today are confident that we are. And we're picking up where Einstein left off in his quest for unification.
Unification would be the formulation of a law that describes perhaps everything in the known universe from one single idea, one master equation. And we think that there might be this master equation because throughout the course of the last 200 years or so, our understanding of the universe has given us a variety of explanations that are all pointing towards one spot. They seem to all be converging on one nugget of an idea that we're still trying to find.
Unification is where it's at. Unification is what we're trying to accomplish. The whole aim of fundamental physics is to see more and more of the world's phenomena in terms of fewer and fewer and simpler principles.
We feel as physicists that if we can explain a wide number of phenomena in a very simple manner, that's somehow progress. There is almost an emotional aspect to the way in which the great theories in physics sort of encompass a wide variety of apparently different physical phenomena. So this idea that we should be aiming to unify our understanding is inherent, essentially, to the whole way in which this kind of science progresses.
And long before Einstein, the quest for unification began with the most famous accident in the history of science.
As the story goes, one day in 1665, a young man was sitting under a tree when all of a sudden he saw an apple fall from above. And with the fall of that apple, Isaac Newton revolutionized our picture of the universe.
In an audacious proposal for his time, Newton proclaimed that the force pulling apples to the ground and the force keeping the moon in orbit around the Earth were actually one and the same. In one fell swoop, Newton unified the heavens and the Earth in a single theory he called gravity.
The unification of the celestial with the terrestrial, that the same laws that govern the planets in their motions govern the tides and the falling of fruit here on Earth. It was a fantastic unification of our picture of nature.
Gravity was the first force to be understood scientifically, though three more would eventually follow. And although Newton discovered his law of gravity more than 300 years ago, his equations describing this force make such accurate predictions that we still make use of them today.
In fact, scientists needed nothing more than Newton's equations to plot the course of a rocket that landed men on the moon. Yet, there was a problem. While his laws described the strength of gravity with great accuracy, Newton was harboring an embarrassing secret. He had no idea how gravity actually works. For nearly 250 years, scientists were content to look the other way when confronted with this mystery. But in the early 1900s, an unknown clerk working in the Swiss patent office would change all that. While reviewing patent applications, Albert Einstein was also pondering the behavior of light. And little did Einstein know that his musings on light would lead him to solve Newton's mystery of what gravity is. At the age of 26, Einstein made a startling discovery: that the velocity of light is a kind of cosmic speed limit a speed that nothing in the universe can exceed. But no sooner had the young Einstein published this idea than he found himself squaring off with the father of gravity. The trouble was, the idea that nothing can go faster than the speed of light flew in the face of Newton's picture of gravity. To understand this conflict, we have to run a few experiments. And to begin with, let's create a cosmic catastrophe. Imagine that all of a sudden, and without any warning, the sun vaporizes and completely disappears. Now, let's replay that catastrophe and see what effect it would have on the planets according to Newton. Newton's theory predicts that with the destruction of the sun, the planets would immediately fly out of their orbits, careening off into space. In other words, Newton thought that gravity was a force that acts instantaneously across any distance, and so we would immediately feel the effect of the sun's destruction. But Einstein saw a big problem with Newton's theory. A problem that arose from his work with light. Einstein knew light doesn't travel instantaneously. In fact, it takes 8 minutes for the sun's rays to travel the 93 million miles to the Earth. And since he had shown that nothing, not even gravity, can travel faster than light, how could the Earth be released from orbit before the darkness resulting from the sun's disappearance reached our eyes? To the young upstart from the Swiss Patent Office, anything outrunning light was impossible. And that meant the 250-year-old Newtonian picture of gravity was wrong.
If Newton is wrong, then why do the planets stay up? Because remember, the triumph of Newton's equations come from the quest to understand the planets and the stars. In particular, the problem of why do the planets have the orbits that they do. And with Newton's equations, you can calculate the way that the planets will move. Einstein's got to resolve this dilemma.
In his late 20s, Einstein had to come up with a new picture of the universe in which gravity does not exceed the cosmic speed limit. Still working his day job in the patent office, Einstein embarked on a solitary quest to solve this mystery. After nearly 10 years of racking his brain, he found the answer in a new kind of unification.
Einstein came to think of the three dimensions of space and the single dimension of time as bound together in a single fabric of space-time. It was his hope that by understanding the geometry of this four-dimensional fabric of space-time, that he could simply talk about things moving along surfaces in this space-time fabric.
Like the surface of a trampoline, this unified fabric is warped and stretched by heavy objects like planets and stars. And it's this warping or curving of space-time that creates what we feel as gravity. A planet like the Earth is kept in orbit not because the sun reaches out and instantaneously grabs hold of it, as in Newton's theory, but simply because it follows curves in the spatial fabric caused by the sun's presence. So, with this new understanding of gravity, let's rerun the cosmic catastrophe. Let's see what happens now if the sun disappears. The gravitational disturbance that results will form a wave that travels across the spatial fabric in much the same way that a pebble dropped into a pond makes ripples that travel across the surface of the water. So we wouldn't feel a change in our orbit around the sun until this wave reached the Earth. What's more, Einstein calculated that these ripples of gravity travel at exactly the speed of light. And so, with this new approach, Einstein resolved the conflict with Newton over how fast gravity travels. And more than that, Einstein gave the world a new picture for what the force of gravity actually is. Its warps and curves in the fabric of space and time. Einstein called this new picture of gravity general relativity. And within a few short years, Albert Einstein became a household name.
Einstein was like a rock star in his day. He was one of the most widely known and recognizable figures alive. He and perhaps Charlie Chaplin were the reigning kings of the popular media.
People followed his work, and they were anticipating, because of this wonderful thing he had done with general relativity, this recasting the laws of gravity out of his head. There was the thought he could do it again, and people want to be in on that.
Despite all that he had achieved, Einstein wasn't satisfied. He immediately set his sights on an even grander goal, the unification of his new picture of gravity with the only other force known at the time, electromagnetism. Now, electromagnetism is a force that had itself been unified only a few decades earlier. In the mid-1800s, electricity and magnetism were sparking scientists' interest. These two forces seemed to share a curious relationship that inventors like Samuel Morse were taking advantage of in newfangled devices such as the telegraph. An electrical pulse sent through a telegraph wire to a map thousands of miles away produced the familiar dots and dashes of Morse code that allowed messages to be transmitted across the continent in a fraction of a second. Although the telegraph was a sensation, the fundamental science driving it remained something of a mystery. But to a Scottish scientist named James Clerk Maxwell, the relationship between electricity and magnetism was so obvious in nature that it demanded unification. If you've ever been on top of a mountain during a thunderstorm, you'll get the idea of how electricity and magnetism are closely related. When a stream of electrically charged particles flows, like in a bolt of lightning, it creates a magnetic field, and you can see evidence of this on a compass. Obsessed with this relationship, the Scot was determined to explain the connection between electricity and magnetism in the language of mathematics. Casting new light on the subject, Maxwell devised a set of 4 elegant mathematical equations that unified electricity and magnetism in a single force called electromagnetism. And like Isaac Newton before him, Maxwell's unification took science a step closer to cracking the code of the universe.
That was really the remarkable thing, that these different phenomena were really connected in this way. And it's another example of diverse phenomena coming from a single underlying building block or a single underlying principle.
Imagine that everything that you can think of which has to do with electricity and magnetism can all be written in 4 very simple equations. Isn't that incredible? Isn't that amazing? I call that elegant.
Einstein thought that this was one of the triumphant moments of all of physics and admired Maxwell hugely for what he had done.
About 50 years after Maxwell unified electricity and magnetism, Einstein was confident
that if he could unify his new theory of gravity with Maxwell's electromagnetism, he'd be able to formulate a master equation that could describe everything, the entire universe.
Einstein clearly believes that the universe has an overall grand and beautiful pattern to the way that it works. And so to answer the question, why was he looking for the unification? I think the answer is simply that Einstein is one of those physicists who really wants to know the mind of God, which means the entire picture.
Okay, that's just good saying to stop. So, for our purposes, how we want to approach this will be as follows. So, when we look at that, what we consider a force of gravity, okay, that meaning as follows here. So when we look at space-time, and when you picture the fabric of the universe, if the sun is sitting in the center, which it is, okay, so it might not be just gravity between two objects that would cause that to stay in orbit. Just like when we think of the Earth and the Moon, you have two objects that have gravity occurring on one another. But if the sun sits in the center of the universe, which it does, we could say that it warps that fabric of space-time. So since it does, it's like it creates a bowl sitting there. So then as the Earth is spinning around in that bowl, it just doesn't have enough energy to escape that. And you wouldn't want that anyway, because if we go further away from the sun, what's going to happen?
Colder.
It's going to get a lot colder.
It's gonna be colder than it is in
Oh,
gonna have to get some.
and that's probably true too. But the problem with that is it just would not be able to support life. So then when you look at how are gravity and electromagnetism related, well, we know that the center of an atom is going to probably get into the strong force eventually. So we'll just keep this as simple as possible. If we're talking about the atom helium, okay, because we don't want to do two atoms of helium, because that would be too funny. You know why? That would be he.
That is my goal.
Okay, so that's why we don't want to do two atoms. We just want to do one. Okay. So one of the things, so you're pointing at Bob or the periodic table. That's what we want you to do. So when you find helium, what is that little number in the bottom left-hand corner?
2.
That means it's got 2 protons here in the middle. Okay. So do we know what type of charge do protons have? They have a positive charge. Okay. So that means there's 2 protons in this nucleus. There's also 2 neutrons. We're not too concerned about that. But if the protons have a positive charge, there must be something that has a negative charge that would balance that out to 0.
Gravity.
No, it's not protons. We counted for those. We said don't worry about the neutrons. There's one more that you haven't mentioned, but you probably have heard of it before.
Static friction.
Electrons. So, just like with our universe, we have this orbital that goes in an orbit that has 2 of these electrons moving around. Okay? And they really can't escape one another. Okay? Because those 2 protons have an electromagnetic effect on these electrons. So they can't leave. Okay? And they can't get any closer because the energy involved moving around this shell keeps them in orbit. And that's why we call that an electromagnetic force. Okay? So anytime you have electricity, you're plugging your laptops into the wall. It's a flow of these electrons through materials. That's what provides electricity. All right? So that's just as good a place as any to stop, so we'll continue with this. We gotta get the afternoon session caught up, which will not take long. I think there's just a couple of groups left. Then we'll continue with this tomorrow, and then we'll see once what shakes out next week. We'll have more of an idea tomorrow. We'll catch up to you next time.